Hey Panthers, it's Mrs. Sherburne, and I'm back for the last demonstration and types of chemical reactions. If you haven't taken a look at the first 4 videos, I did a demonstration and we talked through a single replacement, double replacement, combination, and decomposition reaction. Today we're going to focus on the combustion reaction. I really did save the best for last. So as we go through this demonstration, I want you to be thinking about how are we going to balance this equation, what reaction type it is, and I've kind of spoiled that already. It's the combustion reaction, and we're going to draw a particle model for this reaction. Okay, so come on over here, and I have 70% isopropyl alcohol, also known as propanol, and I really just want, and this is just an empty vinegar container. A few safety measures that I've taken into account to do this demonstration here. I've seen teachers do this demonstration with methanol. That is much more flammable and dangerous to use than isopropyl alcohol would be. I've got my safety gear on, so I'm just going to add a little bit of rubbing alcohol to the inside of this bottle. And then I'm going to shake this up. Most of you know that the fumes of a fuel are a lot more dangerous and combustible than the liquid itself. So I want to get as much isopropyl alcohol in the gaseous form as possible. I do want to also move the container, even though there's not that much left, out of the way. All right, so I've got a wooden dowel and I've taped a piece of kind of like a popsicle stick on the end. This is gonna allow me to not be so close when I bring the flame near the opening of the bottle. All right, here we go. And as I cap the bottle and keep any more oxygen from coming in here, can you see that the bottle is starting to collapse in on itself also? The bottle's really, really quite warm. And then, let me turn the lights back on. I want to point out something when I open the lid back up. Now I know I didn't put that much rubbing alcohol in here. So let's talk about this reaction and the chemistry behind it. So I have on the top propanol, which is the rubbing alcohol, burns with oxygen to produce carbon dioxide and water. And I've got the formulas written out for each. I always, if we were in class, I'd have a student say to me, let's do it again, do that again. And if you look at our products, what's the liquid? The liquid's water. That's not flammable. The gas that was generated inside is carbon dioxide. That's one of the ingredients in a fire extinguisher. So unless we do some things differently, repeating this right away is not something you're going to be able to do. But let's take a look right away. I'm seeing, as we're trying to balance this equation, the red color really stands out to me, that I have 3 carbons over here and I only have 1 over on this side. So if you were thinking, well, we're going to need 3 of those, 3 carbon dioxides, I agree. So let's draw in 3 carbon dioxides. And Okay, and how about if we take a look at hydrogens next? So on my hydrogen side, I have 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 hydrogens on this side, so I'm gonna need 8 hydrogens on this side. So how many total water molecules am I gonna need to draw? If you're thinking 4, you're right. All right, so my H's are good, my carbons are good. Let's see about oxygens now. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 oxygens on this side. But on this side, I still have an oxygen that's in here. So what sometimes happens when we do these reactions is you have to kind of go back to the beginning and almost double what you started with. So if I just drew 5 total oxygen molecules here, I'd have 11 total on this side. 11 does not balance with 10. But a trick that sometimes works is to go back and let's redraw one of these, which also means I'm going to need 6 total of these and 8 total of these. I'll go ahead and do that right now. All right, I have my propanol doubled. I drew twice as many carbon dioxides and I drew twice as many waters. And the last thing, I think, we've got 6 carbons. There's 6 carbons now. There are, I guess we should probably check our H's. 2, 4, 6, 8, 10, 12, 14, 16. And over here, if I have 8 here and then 8 more, my H's are good. I have 16 over there also. If you were wondering why this H isn't written with this H, why the formula is not C3H8O, it's because this OH is what identifies this compound as being an alcohol. So that's why the OH is left on its own. All right, so let's count up our O's. Over here, I've got 2, 4, 6, 8, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20 oxygens. On this side, I have 20 oxygens. So on this side, I need 20 oxygens. So I've got 2 right there. 20 minus 2 is 18. So in here, I need 18 oxygens, and they come in pairs. So if you're thinking, how many molecules do I need to have drawn in this box? If you're thinking 9, then you are absolutely right. So if I can do that quickly. 2, 3, 4, 5, 6, 2, I lost count. 2, 4, 6, 7, 8, 9 oxygen molecules. So I'm going to put that number right here because that's where it's going to go. 9 oxygen molecules. How many propanol or rubbing alcohol molecules did we draw? 2. How many carbon dioxides did we draw? I think we said 6. And for waters, I think we drew 8. 2, 9, 6, 8. Those 4 numbers together cannot be reduced down anymore. So this is my balanced equation. Hopefully our goal will be to be able to do this without having to draw a picture. But I think as we start, the picture can be really helpful. All right, so this is a combustion reaction. I hope you enjoyed it. Please don't try it at home. And I will be in touch, Panthers.